Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. In today's video, we talk about Normalized Mutual Information, or NMI for short. NMI provides a quantitative assessment of a clustering algorithm's ability to identify meaningful and distinct groups within the data. What this means is that after running a clustering algorithm, you get a set of predicted labels, and now you may have access to some external information about the ground truth class assignments. And now you want to measure the agreement between these two sets of assignments that we call them here U and V. And we assume that we have n data points. So this is different than classification problems, because in classification problems, we are using labels for the training data points during the training process. Whereas in clustering problems, we are not using ground truth labels during the training process because they are unsupervised learning problems. And what this means is that when you're running clustering algorithms and you get predictions, the absolute values of labels do not matter at all. And what really matters is that which data points belong to the same cluster. And in that sense, we have always a label ambiguity problem. And therefore, we have to use tools from information theory, such as entropy and mutual information, to find the agreement between two sets of assignments. And we call them here U and V, and each one is length n. So we need to start by the definition of entropy. So it's very easy to remember what entropy is. It's this formula, which is negative sum of some probabilities times log of probabilities. And so what is this summation? This summation goes from 1 to this absolute value of U, and this means that the number of unique labels that you have in U. In the case of clustering problems, you mainly set the number of clusters yourself. So this would be defined in advance. For example, when you run k-means clustering, you say that I want to recover 5 clusters or 3 clusters. And what is this PI? So the PI is, in this case, the probability that an object picked at random from U falls into class UI. So this means that you're going to count how many data points do you have that they have labeled UI, and then you divide this number by the total number of data points that you have, or length of the assignment vector that you have. So what does this mean? So in this video, we're going to talk about also implementing these in Python. So we're going to start by importing NumPy as NP. I'm importing matplotlib for visualization. So in the case that, let's say, I only have 2 unique values, right? In this case, I can just write this entropy as negative p times log of p. And remember, because this is information theory, the base of the logarithm is 2. And then because we only have 2 classes, then the other probability should be 1 minus p, and then times log of 1 minus p. And because probability is always from 0 to 1, and I want to avoid those two 0 and 1, the problems, because I don't want to run into problems with this log, I want to plot this entropy from 0.01 to 0.99. And I'm choosing 1,000 different values, plugging into this entropy and looking at the shape of this entropy. And you can see here that the entropy is obviously 0 when the probability is 0 and 1, and it achieves its maximum at 0.5. And this makes sense, right? Think about it as flipping a coin. You have the maximum amount of uncertainty or information when you have the highest level of uncertainty. If you know that the coin is always, when you flip a coin, you get heads or tails, there's no uncertainty, right? So there's no information. But once you don't know, then you have to have this, 1 unit of information, which is 0 or 1, or heads and tails. So that's the idea of entropy. So now you know that entropy, you can define entropy for also the other assignment vector that you have, which we call it here V. And the formula is exactly the same as we had before, except the fact now we apply this to the assignment vector V, and it is negative sum of probabilities times log of probabilities. So Also, we know that this base of this logarithm is 2. And very similarly, this P prime is the probability that an object from this assignment vector V falls into Vj. And that's why we have this division by the total number of data points. So the second thing that we need to define here is the mutual information between U and V, between these two sets of assignments. So here, because it's a mutual information, so it's a pairwise type of operation, and therefore we have a double summation. The first one is over the labels for the first assignment vector, and the other one is for the labels for the second assignment vector. And then we have these joint distributions, Pijs, which is the probability that an object picked at random falls into class Ui and Vj. And that's why here we show using this intersection notation. And here, look at that, and you can see that we have this Pij, this joint distribution before the logarithm, and also in the numerator of what we have in front of this logarithm. So that's how we define mutual information. And then we have these individual, or I would call it marginalized distributions in the denominator. And then what is the normalized mutual information? It's a mutual information that has been normalized, right? Which means that we have this mutual information in the numerator, and then we have the mean or average of the entropy of U and V in the denominator. So what we want to do here is to implement this from scratch in Python. We have all the tools that we need to implement this. So we're going to start by importing NumPy as NP. And then here, I want to also compare my own implementation with the Scikit-learn's Normalized Mutual Info Score, which is something that you can use. But here, the goal is to really understand how this works and what happens in the background. So in order to show this example, we're going to work with two arrays of labels or assignments. So the first one is 1, 1, 1, and 0. So this means that we have 4 data points. The first 3 ones belong to the same cluster, and the last one belongs to a different cluster. And then we have the second assignment vector. So these are the U and V that we had previously. And in this case, the first 2 data points belong to one cluster, and the last 2 points belong to the different cluster. So we want to know what is the the agreement between these two. And something that also I want to mention is that based on this definition of normalized mutual information, this is a value between 0 and 1. So if it was a perfect match, right, meaning that, for example, in this case, if in this case we have these 3 data points belong to the same cluster and last one to a different one, then we should have got exactly 1. But in this case, we know that we will get something smaller than 1 because we obviously don't have 100% or a perfect match. So how can you define your normalized mutual information? So I'm defining my own function, calculate NMI, which accepts 2 arrays, right? And the very first thing that you need to do is to create a joint probability matrix. What this means is that you need to find a matrix where each row corresponds to one class from array 1, and each column corresponds to one class from array 2, right? And now you want to represent the joint occurrences of unique values from both arrays. So the very first thing that we do, we create an empty, or I would say it's better to say that a matrix where the number of rows is the number of unique classes that we have in array 1. So that's the absolute value of U that we had before. And then the number of unique class labels or cluster labels that we have in array 2. So once we create a matrix of all zeros with these 2 dimensions, now we can start filling it out by counting the joint occurrences of unique values. And for doing this, you can just find this n that we had before, the number of samples that we have in each array, or the length of each array. For doing this, we can just look at length of one of these arrays. And then we are going to add 1 to each of these locations that we have here that correspond to one label from array 1 and then the other label from array 2. And because of the probabilities that we had before, we need to divide these joint occurrences by n. Here we are dividing this joint probability matrix by n. So how does this part work? I have this part, these code snippets to show you how this works. So these are the two arrays that we have here. You can see that we actually have the same arrays. And so we start by having these 2 by 2 matrix where we fill all the entries by zeros. And now we're going to use that for loop that we had to find the joint occurrences of labels that we have. So what this means is that we don't have any 0 and 0 from both of these arrays, right? So meaning that if we look at these 4 locations, we don't have any place that we have 0 in one and then the corresponding 0 in the other array, right? But we have that for 1 and 0, 0 and 1. And actually for 0 and 1, you can see that we have sort of like one of them. And then for 1 and 0, we have 2 of them, right? So you can see that for 1 and 0, which is this one, we have 2 of them. And then for 1 and 1, we have one scenario or one occurrence, right? So that's how you form this, and you get the 4 locations that you have there. And then you divide this by the total number of data points that you have. So now you have all the probabilities that you need in your problem. So we are very much really done here. That's like the main part of this implementation. But going back to the original function that we have to show you the next step is that we need to find those marginal probabilities that we had, right? Like pi and p prime that we had before. And for doing this, we can, in the first case, find the sum of elements across each row. And then for here, we find the sum of these metrics across each column. That's why we are using this axis 1 and axis 0. So these are the marginal probabilities. And in order to find the entropies, we need to look at the negative sum of probabilities times log of probabilities. So these are the entropies that we have. We can show you how this works here. So if we look at it, so these are the marginal probabilities that we have. So the first one is the probability for the array 1, the PIs. And then the second one, that's why I'm here printing this in the next line. You can see that we get this half and half. And now we're looking at the entropies, right? So negative sum of probabilities times log of probabilities. And you can see that in this case, for the first case, the entropy is around 0.8, and the second case is exactly 1. And this is consistent with what we know, right? If we have 2 classes and the probability for each class is 0.5, that's the maximum uncertainty or information. And we showed you in the earlier figure that this entropy corresponding to this is exactly 1. Okay, so now that we have the individual entropies, we need to find the mutual information. And the way that we can do this, remember that we had that double summation in the problem, right? We have a double summation over the unique labels for each assignment. And for now, you can see that we can, write this as 2 for loops if you want to implement this in a simple way. Over the number of unique elements. And if the probability, the joint probability is greater than 0, because if not, we're going to run into problems with log and having 0 inside log. So we don't want to work with if this joint probability is exactly 0, but if not, then we want to plug it into the formula that we have. The joint probability times then log of the joint probability over the marginal probabilities that we have, right? That is what we have in this formulation that we have here. The joint probabilities, log of joint probabilities over individual or marginal probabilities. And to show you how this works, right? So you can see that that's the 2 for loops that we have. And now we can see that this mutual information between between the two assignments is this number, which is almost 0.31. But remember, this is the mutual information, but still it's not normalized. So now we have to normalize this number by the average of these two numbers that we have here. And in order to do that, it's very simple, right? So we can just divide mutual information by sum of these two entropies and then divided by 2. And if we do this, we get this 0.34, right? So this shows that the assignment, the agreement between these two assignments is about 0.34. And let's see how this works. So if we look at this function that we have, so we have all these steps together, right? Creating the joint occurrences of unique values, the marginal probabilities, the entropies, mutual information, and then the final formula that we have for NMI. And in this case, we have the manual NMI, what we just implemented here, and then the Scikit-learn's NMI, or normalized mutual information, using this class, the normalized mutual info score, right? That's the name of it in Scikit-learn. And if we run this and compare these two, you can see that we get exactly identical results, which is great, right? It shows that now we understand how normalized mutual information works in Scikit-learn. Thank you very much for your attention.